Why, hello and welcome to AP Chem video. Dun 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 dun. See, now that's a theme song. That's Star Wars in case you didn't know. Okay, so I'm going to continue on from what Ms. Schneider talked about in the first video. One thing I wanted to make very clear is that if a reaction is spontaneous, then delta G is negative, okay, which means it's favorable. However, that says nothing about how quickly the reaction takes place. So I wanted to remind you that the speed for which a reaction takes place, that is all governed by kinetics, which really in a nutshell is governed by that hill. You guys remember that? That activation energy. Is the hill really big or is the hill really small? That's going to govern how quickly the reaction takes place. So something can have the most favorable delta G in the world, but if its activation energy is high for totally other reasons, then it's just not going to happen very fast. Okay, but today, what we're about to talk about is probably the most important part of Chapter 17. It's this formula that Ms. Schneider talked about. Delta G equals delta H minus T times delta S. So it's relating the exo-endothermic piece with the entropy or disorder piece. But making predictions as to whether delta G will be positive, negative, or what. Okay, so we're going to summarize all the big possibilities. Okay, so the first example I already started for you. So if delta H is negative, that means it's exothermic. Okay, so that means we're releasing energy, and that's always a favorable thing. Okay, we're releasing energy, and that's creating more disorder in the universe, if you will. So exothermic is always favorable. All right, but what if the process also has an increase in disorder? So that means we're also becoming more random, more disorderly. Okay, that is like awesome, 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 very favorable reaction. So what you can say is that, thinking about it mathematically, if this is negative and this is positive, okay, but that negative right there will change the sign, so that's going to make this whole piece negative, then a negative plus a negative can only be delta G is negative, okay? And delta G being negative is spontaneous, or sometimes we just say thermodynamically driven. Okay, so it's driven by the thermodynamics, which is this formula. So we would say in this situation it would be spontaneous at all temperatures, all the time. So for instance, a combustion reaction fits the bill. It releases heat and it creates more disorder. So combustion reactions are always spontaneous no matter what. All right, so here's kind of our opposite situation. What if the reaction is endothermic, so it's absorbing energy from the universe, and there's a decrease in disorder? No matter what, this is not favorable for any reasons, not for enthalpy reasons or for entropy reasons. So no matter what, think about the math. Delta H is positive, which is bad, and delta S is negative, which is bad, and a negative times a negative makes this whole piece positive. Mathematically, a positive plus a positive has to equal a positive. So in this scenario, delta G would be positive. This is never spontaneous. So if you have a process for which these numbers fit, then it doesn't mean that reaction can't happen. It's just you have to do a lot of work to make it happen. And we'll talk about some examples in a minute. All right, the next two examples are a little bit hairy. So let's say a reaction is exothermic, so it's releasing energy, increasing the disorder of the universe, but it actually has negative disorder. So the process, for whatever reason, is creating more order. Okay, so a decrease in disorder. So this piece is good, this piece is bad. So what we would say is that sometimes it can be spontaneous, but sometimes it's not. So let's think about under what situation would it be spontaneous. So let's see, this is negative, so that's a good thing. But this is negative, so negative times a negative, this whole piece is positive. So under what situations, under what temperature is this going to be spontaneous? Are we going to make this negative? Okay, well the key is that to be spontaneous, delta H, the good part, we have to emphasize the good part, has to be numerically larger than T times delta S. Okay, well delta H and delta S are pretty much standard values. So the only thing you can really change here is the temperature. So what temperature are we going to get a negative delta G? So and the key is that you want that temperature to be low. So if the temperature is low, then a small number times this bad delta S is not going to contribute that much. Delta H will outweigh it. Delta H will be more significant, the good part. Okay, so this can be spontaneous, It can be, delta G can be negative, but only at low temperature. At low temps. Okay, and you're going to see in a minute that we can actually calculate those actual temperatures. Okay, so it could be, delta G could be negative or positive depending on the temperature. Okay, low temperature is going to favor delta G being negative. All right, so you can probably guess what's going to happen next. What if we have just the opposite? So inside negative, negative, we have positive, positive. Well, positive is endothermic. That means energy is going into the system, so that's bad in delta G world. But we are increasing disorder. So we're like making more particles or whatever the case may be. So let's do the math here. So let's see, this is positive, not a good contribution. This is positive, and a negative times a positive makes this whole quantity negative. So how can we emphasize this and de-emphasize this? So what are you going to have to do with the temperature? So this guy can be spontaneous, spontaneous, but at high temperatures. We want to make the T times delta S greater or more significant so it outweighs the delta H. Okay, so we want T times delta S to be greater than delta H numerically. Okay, so again, delta G could be negative, it could be positive, depends on the temperature. High temperature is going to favor a delta G being negative. All right, so let's summarize this. I got kind of a little tool to help you. So Ms. Schneider came up with this one, that if you got negative delta H, and she wanted to point out that like this is a negative sign, and S is positive, negative, then delta G would be negative, like there's a negative sign there. So negative, negative, the delta S is positive, delta G is going to be negative overall. So I like that. That's going to help you. But also, if the H and the S, the delta H and the delta S are opposite sign, then it's either going to be spontaneous all the time or it's never going to be spontaneous. Okay? So if delta H is favorable and delta S is favorable, so negative, positive, then delta G is favorable. So it would be negative. And that might help you remember how the signs work. Okay? If delta H is positive, endothermic, bad. If delta S is negative, creating order, less disorder, bad. So then delta G is bad, okay, which means it's a positive value, okay, which means not spontaneous, not going to happen unless you do a lot of work. All right, so how about down here? If the signs for H and S are the same, so negative, negative, then it can be spontaneous at low temp. So I kind of like this, negative, negative, low temp, right? Negative means low. And then if it's positive, positive, then it's going to be spontaneous at high temp. Positive meaning up, meaning high. Okay, so there's some little tricks to help you guys remember. But of course, most importantly is just being able to wrap your brain around every unique situation and understanding why these signs are the way they are. So let's practice that. All right, so we got a couple scenarios here. I want you guys to figure out basically what's going to be true about delta H, delta S, and then as a result, delta G, under what conditions. Okay, so the first one, and I would suggest let's do the first one together, but then do the next two on your own, and then come back and check the answer on the video. So let's say you got a cold pack. Now, right there, that's a big hint. A cold pack. So how does a cold pack feel? Feels kind of cold. So that must mean, is it an endothermic or exothermic process? Is it absorbing energy from the surroundings, which includes your hand, for which you're touching the cold pack? Or is it releasing energy? So a cold pack feels cold because energy is being taken in from the surroundings. So that is clearly an endothermic process. So delta H is positive. Now what about the disorder here? So a cold pack basically works in the way that you have this like solid and then you crack it open, you know what I mean? And it mixes with the liquid that's in the cold pack. So you get this pure solid mixing with water, a pure liquid. And then you get aqueous solution. So you're making this mixture. What do you think about making a mixture? Does that strike you as increasing disorder or not? And I would say that the entropy is going to be positive. You're making a mixture. All right, so we got positive, positive. So that means it's going to be temperature dependent. Okay, now if you memorize what I told you to remember, positive, positive means it's going to be spontaneous at high temp. Okay, but make sure you understand why. So let's see, this is bad. In delta G world, this is good. So we want to emphasize this. So we want this reaction to happen at higher temperatures where we're emphasizing the disorder part and de-emphasizing the endothermic part. Okay, so delta G is going to be negative or it's spontaneous at high temps. So we would say, if you wanted to, it asked about if it's entropy or enthalpy driven. We would say that this one's entropy driven because it's driven by the disorder and not the ex or endothermic. Okay, so we would say that this guy is entropy driven by the disorder. Okay, let's take a look at the next one. So I'm looking at the reaction, and this is where I would pause and try these yourself and then come back and re-listen to the video. All right, so I'm looking reaction type, yeah, combustion. This is octane, so this is what goes on in your gas tank. So combustion of anything, is that going to be endothermic, absorbing energy, or overall releasing energy? Okay, so hopefully you were thinking exothermic. It's going to release energy. That's how your car runs. What about entropy? Let's see here. So we got 25, 26 gaseous particles, and then 16 plus 18 is 32, 33, 34. So you're going from 27 gaseous particles to 34 gaseous particles. That sounds like an increase in disorder. So that's going to be positive. All right, so basically favorable. Delta S positive, increasing disorder, favorable. So what's the only possibility for delta G? Delta G is going to be negative, spontaneous always, at all temperatures. Okay, so mathematically, this is negative, obviously, and then T times delta S with that opposite sign, this is going to be negative too when you change the sign. So that's going to be spontaneous all the time, very favorable. All right, so what about this one? So we got gaseous water condensing to liquid. So if you're going to go from a crazy gas down to a liquid, you get high energy, and then you go low energy. You got to get rid of the excess. So it kind of sounds strange when you're dealing with phase changes sometimes, but is this an exothermic? Are you releasing energy to go from high energy to low energy, or are you putting energy in? Okay, this is an exothermic process. Okay, you got to release energy to go from gaseous craziness to liquid chillness. Okay, so it's an exothermic process. What about the disorder piece? So let's see, gas going to liquid. Clearly, there's not as much disorder in a liquid sample than in a gas sample. So the disorder is going to be negative. All right, so of course this is our classic case of negative, negative, same sign, same sign. So that means it can be spontaneous, but it's going to be temperature dependent. Negative, negative, low temp. Okay, so it's going to be spontaneous. Delta G is going to be negative at low temp. Why low temp? Remember, you can memorize that great, but you got to understand it. Do we want to emphasize the endothermic or the exothermicness, or do we want to emphasize the lack of disorder or loss of, loss of disorder? So this is kind of the one we want to de-emphasize. So when we do T times delta S, oops, negative delta H, we want to de-emphasize this part and emphasize the exothermicness. So we're going to operate at low temp so that this piece is not as significant and this guy overpowers. Good? We're going to definitely do some more practice with this in class as well. Okay, so go back and re-listen to the video if you need to. Make sure you're very clear on these points. Okay, next piece, of course, in classic AP Chem way, we're going to put numbers to all this gobbledygook. So, first question. If delta H for a reaction, so I'm giving it to you, 10.5, and delta S is 30. Okay, would this process be spontaneous or not? Another way of saying spontaneous, this is some new terminology that the AP curriculum is using a lot. They might like to say thermodynamically driven. So in other words, does it have favorable thermodynamics, aka is delta G negative? Okay, so spontaneous and thermodynamically driven are basically the same thing. Okay, and then you can break that down further, which is what we're talking about here, and I realized I didn't really complete all the statements here, is then within thermodynamically driven, you can say, okay, is it the entropy piece or the enthalpy piece that's really making this happen? So for this guy, since delta H, since it's basically spontaneous always, we'd say it's enthalpy and entropy driven. Okay, so it's driven by both those pieces being favorable, enthalpy and entropy. And this one, okay, so the enthalpy is favorable, the entropy is not, so we would say it's enthalpy driven. Okay? And they're all thermodynamically driven, and you'd have to know more information about the kinetics to decide overall if the reaction is going to happen quickly or not. So that would be talking about speed of reaction kinetically driven. Okay, but we'll get to that later. Okay, so going back to that little problem right here. So basically you're solving for that classic delta G formula. Okay, and it looks something like that. So you know the delta H, and you also know the entropy. Be careful. Units can kill you here. Delta H is typically given in kilojoules per mole, but entropy values are typically given in joules per Kelvin. So what you have to do is you have to make sure and convert them to both kilojoules or both joules, doesn't matter. So I went ahead and converted the 30 joules to kilojoules. So I moved the decimal place over 3 spots. Okay, converted the temperature to Kelvin. So kind of doing the math. And as it turns out, delta G is 1.56 kilojoules for this process. So that means it is not favorable. So delta G is a positive number. It is not spontaneous or not thermodynamically driven. All right, so the next piece, it says, well, at what temperature will this reaction become spontaneous? So assume delta H and delta S, they have that little circle right there. So that means they're based on 25 degrees. They're based on the standard values at the back of the book. So when will it become spontaneous? All right, so the key here is that how do you cross over from spontaneous or not spontaneous to spontaneous? Well, delta G has to be 0 at some point. So basically you can go ahead and set delta G to 0 and solve for the temperature. So delta G equals 0. That's actually equilibrium conditions. We'll talk about that later. And then you can pop in those same values and say, okay, well, at what temperature will this become spontaneous? So when you solve for temperature, it comes up to 350 Kelvin. You can convert that to Celsius. It's at 77 degrees Celsius. So in this case, let's talk about our numbers here. Delta H was positive. Delta S was positive too. Okay, so when positive means at higher temperatures, it's going to become spontaneous. Okay, so given the values we were started with, we were at 25 degrees, so you had to raise the temperature to 77 degrees before, it became actually spontaneous. Okay, until this entropy sort of kicked in and overpowered the delta H. All right, so that's sort of a fun problem. You'll see some of that practice in your book as well. The last one we're going to do deals with phase changes. So phase changes, are when you go from a solid to a liquid or a liquid to a gas, whatever the case may be. So we're going to look at a liquid water going to gaseous water. So you're basically boiling water. So what I want you to do is basically calculate the boiling point of water, but using the delta G formula. Okay? So basically, at what temperature will a sample of liquid water spontaneously turn into a gas? That's basically the boiling point. So again, we're going to set delta G equal to 0. That's actually equilibrium. Okay? And the equilibrium between liquid water and gaseous water is its boiling point. We'll talk more about phase changes later, but at the boiling point of a substance is basically sort of that gray area between liquid and gas. It's when it's changing, it's equilibrium. Okay, so we're going to set that to 0 and then pop in these values. So the heat of vaporization is the amount of energy needed to vaporize a mole of water, and then the delta S for vaporizing. So it's sort of that measure of the disorder that you get when you go from a liquid to a solid. All right, so we pop those numbers in. Going back to what we talked about earlier, this is endothermic, so it's not very favorable, but we're increasing in disorders, so this is favorable. So water boiling is going to happen spontaneously, but only at higher temperatures. Okay, and we're calculating that temperature. So go ahead and calculate it. Temperature comes up to 370, so you guys can do the math, bring that over. So it's minus 44 equals negative temperature times this number and divide both sides. Whatever, make sure you can do the math. And convert that to degrees Celsius, and it comes out to 97 degrees Celsius. Now, it's not perfect, because you guys all know water boils at 100 degrees, but it's pretty close. And I did want to remind you that you needed to convert the joules, entropy measured in joules, to kilojoules, and I actually didn't show that quite properly, so let me fix the units right there. So I moved the decimal place over 3 spots, so it was in kilojoules per mole times Kelvin for the units. All right, so why isn't it quite perfect? Well, keep in mind that anytime you're using the delta G formula and you're using those numbers at the back of the book, or if you see that little circle right there, that means standard conditions. Standard conditions, by definition, are 1 atm and 25 degrees Celsius. Okay, so this is delta H at 25 degrees Celsius. This would be delta S at 25 degrees Celsius. Clearly, we're not at 25 degrees Celsius. We're at close to 100. So these values are sort of an estimate. They do a pretty good job. They got us in the ballpark, but they're not perfect. Okay, so delta H with that little circle and delta S with that little circle are for standard conditions. Okay, 25 degrees Celsius, not 100. All right. Well, that closes us down for this section. For the next section, we're going to get into how equilibrium really plays a role in all this. So if you have any questions, don't hesitate to come in after school or ask questions in class. Thank you for listening. And if you just heard, that was the bell, so I guess I'm officially done.